Hello, this is question 8 from the step 2 paper from 2023. We got a tetrahedron, and a tetrahedron is called isosceles if each pair of edges which do not share a vertex have equal length. Each pair of edges that do not share a vertex have equal length. Okay, I might have to think about that again in a minute. Now, part 1, prove that a tetrahedron is isosceles if and only if, so that's important, all four faces have the same perimeter. Right, so let's go back to what's going on with this tetrahedron then. So tetrahedron, we've got 4 triangles stuck together. So this is going to be hard to draw and make it look anything other than I'm drawing a square with a cross in the middle of it. But there's our tetrahedron. So we've got 4 faces, we've got 6 edges, and we've got 4 corners. Right, so we've got each pair of edges, we've got 6 edges. So we're saying each pair of edges which do not share a vertex have equal length. Right, so let's think about what these are. So if I take that edge, so what does it not share a vertex? So it'd be that one. So those we're saying are the same length. So that'd be one pair. Yeah, because it shares a vertex with all the others. And then if I was looking at this one, it would go with this one. And then the 2 that are cross in the middle are actually not touching each other because one of them is near to us and the other one is far from us. Okay, right, so we've got all of those pairs. I can at least see what they mean by this. So we've got to prove that the tetrahedron is isosceles if and only if all 4 faces have the same perimeter. So we've got to do 2 things then for an if and only if. We need to have if all same perimeter, then it's isosceles. So yeah, if isosceles if and only if they have all the same perimeter, right? So yeah, so if we've got that's doing the if, and then we've got the only if, which I'll put down here then, is if isosceles, then all same perimeter. As in we have to be able to work in both directions if we're gonna have an if and only if. Right, so let's try which one of these is going to be easier, I think, on this. I don't know actually, so I'll just do them in order. Let's start with if all the same perimeter, then is isosceles. So let's label these sides then. So if I had something that was looking like that, so what am I going to call these? So let's call that, let's just go round and say I've got A, B, C at the bottom, and then D, E, F going around there. So I'll just label those 6 sides. So if they've all got the same perimeter, then I'm saying that A plus B plus C is going to be A plus D plus E is going to be, what have I then got? E, C plus E plus F. And then the far side, oops, is going to be equal to B plus D plus F. Okay, right, so that's my 4 faces and my 4 perimeters. Right, so what can I get out of all of these? So I've got 6 pairs of equations here. So I could say that B plus C is D plus E. I could say, so that's just looking at the first 2 and taking the A's out. I could have A plus B is E plus F. I could have A plus C is D plus F. Okay. Do I need to write all of these out? I don't really know if I need to write all these out or not. So, I mean, let's go for, I don't know, maybe, well, let's write some more out while I'm here. It doesn't take long to write them out, does it? A plus D is C plus F. And then I'll get rid of D. A plus E is B plus F. And then get rid of F. So C plus E is B plus D. Right, so on all of these then, I want to now get something. Well, let's just start with these first 2 equations and subtract them. That'll get rid of the B's and the E's. So if I do A minus C is equal to F minus D. Okay. Then what am I doing? Well, I can add those to the bottom one. So yeah, I'm just working off of these three equations here. So add that to the bottom one. I'm going to get 2a is equal to 2f. So I've got a is equal to f, which means that c is equal to d, which means that b is equal to e. Okay, so if all same perimeter, which is that, then isosceles, which is what I've shown. Right, okay, so that's worked fine. If isosceles, then all the same perimeter. Right, so if it was going the other way round, isn't this just going to be obvious if I'm doing it this way? So if it's isosceles, I'm saying that A is F and that B is E and that C is D. So then I'd have A plus B plus C. I'd have, well, I'm going back to these equations over here, aren't I? I then have A plus D plus E, C plus E plus F, and B plus D plus F. So this would be equal to A plus, well, B is the same as, D is the same as C, and E is the same as B. So that's the same. C's fine, E is B, and F is A. And then B is fine, D is C, and F is A. So that's showing all of that. Right, so yeah, that works. So I've done my if, and I've done my only if, and it's all worked out fine. Excellent. Right, so that's part one done. On to part two. Right, let OABC be an isosceles tetrahedron. Let OA equal AOB equals B and OC equals C. Okay, by considering the lengths of OA and BC, show that and show that. Right, so let's get clearer ideas. So we've got OABC. So that's our O. Let's say we were going to A, we were going to B, so that could be like the base of our isosceles tetrahedron, and then we've got C, which would be the peak at the top. So this is A, this is B, and this is C. Right, by considering the lengths of OA and BC, show that. Right, so let's do what they are telling us to do then. So we'd have that the length of A is going to be equal to, so the length of BC, so that is going to be C minus B. Okay, so the length of C minus B. And we need to show all of this. Right, clearly we're squaring loads of stuff. So let's do that. Is going to be equal to that. So that is going to be mod C squared plus the mod of B squared. And then I'm going to have to take off two, well, B dot C, C dot B, whatever. It just seems like, better to put them in alphabetical order. So I'll go with that. Is that it? That might be it, actually, mightn't it? They've just rearranged that. 2B dot C is equal to mod B squared plus mod C squared minus mod A squared. Okay, right, so that dropped out pretty quickly. And then show that. Right, okay, so what are we doing? So this is for an isosceles. Yeah, isosceles tetrahedron. So I've worked out off of those. Do I do it again for A dot, well, I need an A dot B and an A dot C. I've got a B dot C. It feels like I need to do these again for the other sides. It's going to be easy because by symmetry, we can swap the letters around. So it doesn't really matter. We've got nothing special about A, B, or C. So I could do, let's change let's go A dot B. So that is going to be mod A squared plus mod B squared minus mod C squared. And then if I do 2A dot C, that's going to be this. So that's just flipping all the letters around. So is that going to help then? So yeah, because I want to do A dot B plus A dot C. That's what I'm after here, because that's what I've got on the left hand side. So that is going to be a half of, what have I got, mod A squared plus mod B squared minus mod C squared plus mod A squared plus mod C squared. Yeah, these are just going to cancel out. So the B's and C's disappear, and I just get that. All right, okay, that was quite a friendly part of the question. So I get the feeling this is going to just suddenly ramp up, but that's first two bits. Part 3, let G be the centroid of the tetrahedron, defined by OG is that. Show that G is equidistant from all four vertices of the tetrahedron. Okay, so, well, what have we got then? So let's think about this again. So I had my vectors going out like this, didn't I? I had A, I had B, I had C, going from O to A to B to C, and now I've got G is the centroid, so I've got some, let's just stick it there just to make it easy to fit on the picture. So that is, well, let's call that G, seems sensible, doesn't it? Then we've got it equal to that, so I need to show then that is G is equidistant from all four vertices, so I need to show that mod G is equal, need to show that distance there, so from A that's going to be G minus A, from B it will be G minus B, and from C it will be G minus C. Right, okay, well, I mean, it's going to be the same from A, B and C for these symmetry reasons that we've already had. The issue is going to be, is it then going to be the same distance from O as well? I mean, it does seem likely, doesn't it? So, well, obviously it is, because that's what we're trying to show, but it seems on the face of it likely before we've even started. So let's go with, what have I got then? Off of this, I've got that 4G, let's just get rid of that quarter, is A plus B plus C. So what am I going to want to do on this then? Well, I need to work out one of these three things here. One of that one, or that one. If I've done one of them, I've done all of them, as I say, because these A, B's and C's are, I mean, they look like they're just going to be interchangeable. I can't see, I mean, we're starting from a point of symmetry here and we're working through symmetrical arrangements, so I'm thinking when we get to the end it's going to end up being symmetrical as well, but still, let's think about that. So if I had 4 lots of well, let's say G minus A, so let's do this first one here, so I can take 4A off the other side, so that is going to be B plus C, I don't know why I put it in brackets, minus 3A. So I've got that, and now I want to show that the length of these magnitudes are the same. So if I've got 16 mod G minus A, and well, I'm going to end up squaring them, so I might as well put that straight in, because you always end up squaring these things, is then going to be the mod of B plus C minus 3A, and then we can square that. So I'm going to get here, this is going to be a lot of stuff. I'm going to have a mod B squared, I'm going to have a mod C squared, I'm going to have 9 mod A squared, then I'm going to have, well, let's do the B's and C's, I'm going to have 2 lots of those, I'm going to have a 2B dot C, then I'm going to have minus 6A, and then, well, dot B and dot C, so dot B plus C. Okay, so that's all of that. And what do I do now? I mean, I know I've got these things. I mean, they've both cropped up in this, so that seems quite promising, doesn't it? So that is going to be a mod B squared plus a mod C squared plus 9 mod A squared 2bc, so that's plus another mod b squared and another mod c squared minus a mod a squared. And then I've got 6 lots of this, so minus 6 mod a squared. So that is 2 lots of b, 2 lots of c, and 2 lots of a. Excellent. Right, so I've got 2 lots mod b squared plus mod c squared plus, I've run out of space, mod a squared. Right, so that's good, and that fits with the idea of it being biosymmetry. So, you know, we're going to get the same. So biosymmetry, we've got that mod g minus a equals mod g minus b equals mod g minus c. Okay, but I haven't done the mod g bit, so I need to do that. So I'm going to have for the, well, let's go straight off of this again, because that's going to give me 16 mod g. So if I do 16 mod g squared, which I need to show is this 2 lots of mod a squared, mod b squared, mod c squared. So that is going to be mod a plus b plus c squared. So I've got mod a squared plus mod b squared plus mod c squared, and then I'm going to have these like 2 lots of all these other things. So I'm going to have 2 lots of each combo. So a dot b plus a dot c plus b dot c. So what happens when I add all those up? I'm going to have all combos of this. So I'm going to have 2 of each one minus 1 of each one when I do these. So that is going to come out the same. So mod a squared plus mod b squared plus mod c squared. Okay, which equals mod g minus a. Well, it sort of equals that times 16. So therefore we've got, I can then add to the list of all that it equals mod g. So all of them are equidistant. So therefore I'm kind of jumping around the screen there, but g is equidistant from O, A, B and C. Right, that was fine. Again, this is so far so good, I would say, with all of this. All right, part 4, by considering the length of the vector a minus b minus c, or otherwise, I doubt it, show that in an isosceles tetrahedron, none of the angles between pairs of edges which share a vertex can be obtuse. Okay, can any of them be right angles? Right, it's not obvious where this is going, but they have told us to look at the length of that vector. So we want a minus b minus c, and we've been squaring these all the way through. So, well, let's see what we get. So that's going to give us an a squared, a b squared, a c squared. Then we're going to have, well, the a's are going to give us minuses. So we're going to have a minus 2 lots of a dot b and a dot c. So a dot b plus c. Okay, underline all those. And then we're going to have a plus 2 b dot c. Right, so coming back to these things again. So this is giving us the a squared, the b squared, the c squared. Then we've got minus 2 lots of that. So that's minus 2 of a squared. And then we've got the 2bc, which is a plus b squared, a plus c squared, and a minus a squared. So that is what we got. We've got 2b, 2c, and minus 2a. So b squared, c squared, and a minus a squared. Okay. So we've got that. So that's considering the length of that vector. So we've got something to do with this length, or at least the square of the length, and show that none of the angles between pairs of edges which share a vertex can be obtuse. So how is this working? What we got here? We've got a, well, this thing's got to be positive, or at least it could be equal to 0, but it can't be negative. So we've got that. So that's telling us then that we've got this a squared has got to be less than something. Okay. I mean, this has got air of Pythagoras about it, which fits with an idea of right angles and things. So what can we say about this? We've got, yeah, I'm finding it hard to visualize this. Right, so say that was O. Say we were looking at our base, OBA. Let's call that base. So this is our A. This is our B. And because it's isosceles, then this thing here is going to have the length of C. So that's okay. So what am I saying then? So when this turns into, yeah, we're going to get an equality here. When, okay, yeah, I can see where this is going. Right, so if we've got the B squared plus C squared is equal to A squared. So if we've got that, then we're saying that OBA, that angle here, that's going to turn 90 degrees. If we've got that B squared plus C squared is greater than A squared, then so we've, yeah, A is getting smaller. If we started at that 90 degree, we had a right angled triangle. We're now saying that those other two sides are bigger when they're squared and added. So that means we're getting that OBA is less than 90 degrees. So we can't have any obtuse angles, again, through symmetry. So no obtuse angles through symmetry again. There's a lot of symmetry in this one, because we could do exactly the same. We could do the same for all other angles. Yeah, there's no difference here again between A, B, and C. So that's ruled out obtuse angles. So can any of them be right angles? So can we have this case? So what would happen then if we did have that case? Then where would our other corner be? So we've got the, where is C? C is, well, it's C away from O. So we know that much. It's, what is it, away from, oh, it's hard to imagine where everything is now. So it's C away from O, but then, because we had C, say C was up here, that was going up there, wasn't it? Saying we had C going there. So that means from A, it is B away. It's B away from A. And so it must be A away from B. And A away from B. So where does it end up then? Where does it end up? Not really sure. Can that work if you add that? And if it, we're just going to get too many 90 degrees on this. So is it turning flat? I'm trying to. So if we got O, we've got B, and we've got A, and we've got that as 90 degrees there. That is B, that is C, and that is A. Essentially what we're saying there. So if we had to put C in, it's got to be A away from B, B away from A, and C away from O. Yeah, it's just putting it here, isn't it? As in we're putting C there, where that would be B away from A, C away from O, and then A away from B. So we're getting a rectangle. So they're all in the same plane. So that's not really a tetrahedron. I mean, well, I suppose it depends what you class as being a tetrahedron. I mean, really, it's just a rectangle rather than being a tetrahedron. It's got no height, has it? You know, C's got to go in or out of the plane in order to make it a tetrahedron. So how am I going to actually convince anyone of this? This would be, okay, so I'll say first of all forms a rectangle, not a tetrahedron. So then I could say that O, A, B, C in the same plane. Is there anything in the calculations that would have shown this? I mean, it's only working off of this thing here, so that doesn't really help. It's just giving us more 90, or does just saying there's too many 90 degrees. Does that work as well? I mean, that could be a possibility. I could say, well, if OBA is 90 degrees, then I'd also have that OCA is 90 degrees and CAB is 90 degrees, and also whatever the other one is that I haven't written down, BOC is 90 degrees. So that's a possibility of saying, well, they've got to all be in the same plane then if we've got 4 right angles. So that's something else. I've got, just looking back through the other bit of the calculations, it just feels as though I'm kind of short a real knockdown argument here. Well, maybe that is good enough. I don't know. I mean, here I've got this thing is equal to 0. All right, okay, this is going to be better. I can come back to this. Well, I don't know if it is better actually, but it's much the same. I mean, if this is 0, then I'll be saying off of the back of this, yeah, these things are the same. So this means, let's put this in green, that A minus B minus C is equal to 0. So I've got that A is equal to B plus C. So that means they must all be in the same plane. So therefore, A, B, C, all in same plane. Therefore, O, A, B, C, all in same plane. Okay, so yeah, different ways of trying to unpick that bit at the end. I'm not sure that's actually much better than my sketch here in blue. I think that blue bit I think that's fine. I mean, it should, because there's no other way we're going to be able to make all of those distances add up. If we got to have A, B, and C as all of these same distances, it inevitably forms that rectangle. There's no way we can raise C out of the plane if we're thinking of that being our potential peak apex of the tetrahedron. We just can't raise that out of the plane and still keep those distances of A, B, and C away from B, A, and O. So I think that's probably enough. But there's 3 different justifications there. And so the green one coming back to our original length, looking at these angles and saying, well, we've now got 4 90-degree angles. So that's just not going to work to create a tetrahedron. It's only going to create a rectangle. Or this sketch, my initial attempt here showing again, it's got to be a rectangle. So, but yeah, that was a trickier bit at the end. I think the first part was fine. I mean, that was providing you're all right with the if and only if bit, and you do it twice. That first bit was fine. Part 2 was fairly straightforward. 3 was a little more tricky, but not that much more, because we were in the mood for it then. I mean, we've just been doing the same thing all the way through, looking at lengths and squaring them out. And then part 4, again, there's certainly similarities. It's just as well they said do this. I mean, I had no idea what I'd do otherwise on this, but then again, I suppose I haven't really thought about it. But they've pointed us in the right direction by working out the length of that vector. So yeah, not bad question. I mean, when I see the vector ones, I don't necessarily jump in on those. You know, I'll be going for Matrices always seems to be a nice one in these step papers, the two mechanics questions. The stats ones often aren't that bad either. So, and then just pick up some nice looking pure questions. But this one wasn't too bad, you know, a bit geometry. At least there was something to interpret, a bit of insight to give into the question in that last part.